This is section 2.2. It's derivatives. We're looking for a shortcut. So without doing the limit process, we would, if we had done the limit process to something like this and we're looking for its derivative, we would have ended up with, so if we said f of x equals x to the third, and then we were taking its derivative, we would get f prime of x equals 3x to the second. And so we're looking for a pattern here. What mathematicians notice is that basically the 3 came out front, and then we dropped this by 1. So the rule is actually multiplying and then subtracting. So let's look at another example here. Had this been something like 5x to the third and you were looking for its derivative, you would multiply 3 times 5, which is 15x to the second. So you're multiplying and you're subtracting 1 from the power. So the derivative is always going to be 1 degree lower than the original function because you're subtracting 1 from the exponent each time. And again, this is just a pattern that we noticed after taking many, many derivatives using the long limit process. And I want to show you several examples here that are worth noting. So if you had f of x, if this is a polynomial function, x to the third minus 4x plus 5, and you wanted to find the derivative, f prime of x, again, this would be 3x squared, multiplying and subtracting. This is a linear negative 4x, so the slope never changes. The slope is just negative 4. You could think of this as a first power, so you'd actually be multiplying by 1. That's why it stays negative 4. And then you subtract 1 from 1, which is 0, and anything to the 0 power equals 1, so it's negative 4 times 1. But that's a linear, and that's why it's just negative 4. And then this is a constant, and the derivative of a constant is 0, so I don't need to write that. And the reason that the derivative of a constant is 0, because if you had a function f of x equals 5, the graph would look like y equals 5, would just be a straight line, and the slope everywhere would be 0. And so the derivative of a constant is 0. So that's why this just becomes 0. So this is the derivative of this. And that's a polynomial function. I just want to do a bunch of examples for you. If you had f of x equals negative x over 4 plus 3x to the third minus 2x. This is pretty straightforward. I'm looking for the derivative. You could put a 1 here. You would multiply by 4, which the 4's would cancel. You'd have negative 1x to the third, because we dropped the power here, plus 9x squared, because I'm multiplying, and then minus 2. So again, that's a polynomial function. It's pretty straightforward. And you can see, of course, how, imagine if we were doing this out using the limit process. This would have taken a long time to do, especially with this fourth power here and this cubed here. So the shortcut takes seconds to do. So it's really nice to have that. F of x equals 3x squared minus x plus 1 over x. Okay, so in this example, it looks like a quotient, but it's not a quotient. We're going to learn in the next section about products and quotients. They're dealt with separately. They have their own rules called the product rule and the quotient rule. So this looks like a quotient, but it's not, because each of these terms can be rewritten 3x squared over x. So if I wrote it out, it would look like this: 3x squared over x minus x over x plus 1 over x. And of course, this can be reduced to just 3x, because this x's would cancel, minus x over x, which is 1, plus, and you could write this as x to the negative 1. And now you have a polynomial function, which is easy to take its derivative, f prime of x equals, this is a linear, so the derivative is just 3. This is a constant, so its derivative is 0. And then here you would multiply by negative 1, so negative 1x, and then drop this, subtract 1 from here to the negative 2, which can be rewritten as 3 minus 1 over x squared. And that's the derivative. So you would rewrite this into 3 separate terms and then reduce them and then take the derivative. So it looks like a quotient, but it's not a quotient. It can be reduced to a simpler form. Okay, and some other examples. You could have something like f of x equals 5 over 2x cubed. This can be rewritten. So a lot of times you want to rewrite the function before you try to take its derivative. This x to the third, this 5 over 2 is a coefficient. X to the third can be rewritten as x to the negative 3. Now you can multiply and subtract. So f prime of x equals negative 3 times 5 over 2 x to the negative 4. And of course that's negative 15 over 2. And now this x to the negative 4 can be rewritten as x to the 4th in the denominator. Okay, so this is the final answer here. So sometimes you have to rewrite it. In this case, you'd bring the x to the third up. I want to show you another example. I'm running out of room, so I'm going to do it on another sheet. But same example, but had this been in parentheses right here, or maybe I can just do it underneath. Had that been in parentheses, this whole thing is raised to the third, so you would rewrite this problem as 5 times 2x to the negative 3. Or you could even better probably, you know what, I'll do this on the other page. I don't have enough room here, so was it 5 over 2x to the third? 5 over 2x to the third. Even better if you cube it first. In the denominator, you would get 5 over 8x cubed because you're distributing this exponent. And now you can rewrite that as 5 over 8 x to the negative 3, as I did in the previous example. Then multiply and subtract 1. So you'd have negative 15 eighths x to the negative 4, or negative 15 over 8x to the 4th. And that's the final answer. So it takes a few steps, but they're not difficult to do. You just have to do some rewrites. Once you've rewritten it a few times, then you can take the derivative here, which is, again, is just multiplying and subtracting. Okay, any other examples? I guess we'll work the rest out in class. The only other thing I should point out is that the derivative, we're going to work out all the trig functions. We'll do some of these in class, but I just want to mention to you that the derivative of the sine of x is just the cosine of x. And I'll explain further why in class. And the derivative of the cosine of x is negative sine of x. Again, I'll explain that further, but just memorize. This is worth memorizing that the derivative of the sine is the cosine, and the derivative of this cosine is the negative sine. And notice I used a different notation here for derivative. So this says the derivative of the sine of x is the cosine of x. Okay, I think I'm going to stop there, and the rest I'll explain. I'll do more examples in class.